Hello everyone, my name is Kishan Agarwal and today I am going to present my tech talk video of probability and statistics, and my topic is binomial distribution based approach to deriving time series weights. So before going to start our topic, let us discuss what is binomial distribution probability. So what is binomial distribution? If x is a discrete random variable with probability mass function where x is 0, 1, 2, 3, so on up to n, and q is equals to 1 minus p, then x is a binomial variate and the distribution of x is called binomial distribution. So binomial distribution formula is p of x is equals to ncx into p of x into 1 minus p whole power n minus x, where x can have values from 0 to n and q is equals to 1 minus p. So what is binomial distribution? The word binomial literally means two numbers. A binomial distribution for a random variable x known as binomial variate is one which there are only two possible outcomes, success and failure, for a finite number of trials. Note that however we define success and failure, the two events must be mutually exclusive and complementary. That is, they cannot occur at the same time, mutually exclusive, and the sum of the probability is 100%. That is complementary. So this is the formula of binomial distribution, that is p of x equal to x is equals to ncx into p power x into q power n minus x, that is q can be written as 1 minus p whole power n minus x. So here a capital X denotes the random variable and x denotes the number of success, and here c is the combination of x successes per p trials, and p is the probability of success and q is the probability of failure. So q can be written as we know that p plus q equal to 1, that is probability of success plus probability of failure is equals to 1. So probability of failure can be written as 1 minus p, and n minus x denotes the number of failures. Now assumptions for binomial distribution. So there are some assumptions before we are finding the binomial distribution. They are, for each trial there are only two possible outcomes, that is success and failure, and the number of trials n is always finite. For each trial the two outcomes are mutually exclusive and p of s should be equal to p, which is a constant, that is p of f, that is probability of failure, is equals to q, that can be written as 1 minus p. The trials are independent. The outcome of a trial is not affected by the outcome of any other trial. The probability of success p is constant from trial to trial. So these are some assumptions which we consider to find a binomial distribution table. So let's begin with our topic, the time series using binomial distribution. So information aggregation is an essential process in many fields like mathematics, economics, biology, engineering, mathematics, medicine and military affairs, etc. A variety of techniques have been developed to aggregate, augment information collected at the same period. However, it seems that there is a little investigation on the aggregation process of arguments collected at different periods, in which time series weight plays an important role and thus should be highly emphasized. In this video, I am going to introduce a time series weighted aggregation, that is TSWA, time series weighted aggregation operator, and for purpose of an approach based on the binomial distribution probability density function and its inverse form to deriving the time series weighted associated with the time series weighted aggregation operator. Then we give a detailed analysis of the properties of the derived time series weights. So, introduction to the topic. Information aggregation is an essential process and is an important research topic in the field of information fusion. It is basically consists of the two following parts. That is, first one is collect argument information and the other is fuse argument information. So collect argument information. The argument information is either collected at the same period or collected at the different periods. Next, fuse the argument information by using proper information fusion techniques. That is, throughout this paper we call them information aggregation operators. Over the last decades, information fusion has been widely studied and many aggregation operators have been developed to fuse various different types of arguments information, which can be classified briefly in the following four categories. So the first category is the operators that can only be used in the situations where the arguments are exact numeric variables, such as the weighted averaging operator, ordered weighted averaging operator, weighted geometric operator, ordered weighted geometric operator, generalized order weighted averaging operator, weighted ordered weighting average operator, and hybrid weighted aggregation operator, etc. The operators that can only be used in situations where the arguments are inexact numeric variables, interval values and fuzzy values, etc., such as the fuzzy weighted averaging operator, uncertain ordered weighting averaging operator, continuous ordered weighting averaging operator, continuous ordered weighted geometric operators, and fuzzy ordered weighted geometric operators. These are the second types of variables or arguments which we use in the time weighted series. The third and the most important are the operators that can be used only in situations where the arguments are linguistic numeric variables, such as the linguistic weighted averaging operator, linguistic ordered weighted averaging operator, extension principle based linguistic aggregation operator, symbol based linguistic aggregation operator, tuple aggregation operator, linguistic weighted ordered weighted averaging operator, ordinal ordered weighted averaging operator, ordinal linguistic aggregation operator, linguistic hybrid aggregation operator, induced linguistic ordered weighted averaging operator, uncertain linguistic weighted averaging operator, uncertain linguistic ordered weighted averaging operator, induced uncertain linguistic operator, uncertain linguistic hybrid aggregation operator, generalized induced linguistic aggregation operator. These are the arguments which are used only in the linguistic numeric variables. And the last type is the operator that can be used, that can be provided for aggregations in environments which mix linguistic and numeric variables, such as the maximum and minimum operators, induced ordered weighted averaging operators, induced ordered weighted geometric operators, generalized induced ordered weighted averaging operators, and generalized induced ordered weighted aggregation operators. So current research on aggregation operators mainly focuses on time independent aggregation operators. So these time independent aggregation operators have been proposed for aggregating argument information collected at the same period and thus do not take time into account. So consider that in many practical applications such as multi-stage investment decision making and personal dynamic examination, etc., the argument information is usually provided at different periods and thus time series weights, that is, weights of all the periods, plays an important role in aggregation process of argument information. Therefore, we need to develop some time dependent aggregation operators in which time series weights should be highly emphasized. So for that we use binomial distribution approach because it is very easier and it is very near to it. That means it easily gives us the answer. We first define the concept of a time series weighted aggregation, that is TSWA, time series weighted aggregation operator. So definition for the binomial distribution based approach. So we are going to assume A, that is A of Tk, where k can have values of 1, 2, 3 up to p, and it is a collection of p, that is p is always greater than or equal to 2 arguments collected at p different periods, that is tk, and here tk again have the values of 1 to p, and let w of t, which is equals to w of t1 comma w of t2 comma w of t3 so on up to w of tp whole power t be the weight vector of the period tk. So then we call as time series weighted aggregation of a of t1, a of t2 so on up to a of tp is equals to summation of k equal to 1 to p w of tk into a of tk. That is the collection of period arguments into the weight vector. So we are getting the time weighted aggregation operator or time series weighted aggregation operator. So a time series weighted aggregation operator is only satisfied when the condition, that is w, that is weight vector of kth period, should be always greater than or equal to 0, and k value should hold the values of 1 to p, and summation of all the weight vectors of period k should be equal to 1. So these are the three conditions we are going to take when we are discussing or deriving the definition of time series weighted aggregation operator. Next, weight vector, that is w of t, which is equals to w of t1, w of t2, w of tp in in this vector, the binomial distribution is one of the most commonly used probability distribution which arises in many practical situations such as quality control, public opinion surveys, medical research and insurance problems, etc. In statistics, the binomial distribution describes the possible number of times that a particular observation will succeed in a sequence of observations. The observation is binary and it may succeed or may fail. The binomial distribution is specified by the number of observations, p minus 1, and the probability of occurrence, which is denoted by u. It is a discrete probability function, which is p of z equals to k is equals to p minus 1 ck u power k into 1 minus u whole power p minus 1 minus k. So here it is similar to the NCX, where n is equals to p minus 1 and x is equals to k, and probability of success is denoted by u and probability of failure is denoted by 1 minus u, where k has the values of 0 to p minus 1. Next, obtaining exactly k successes in p minus 1 observations, where p of z equal to k is the probability of exactly k successes and p minus 1 ck is a binomial coefficient with p minus 1 ck is equal to p minus 1 factorial by k factorial into p minus 1 minus k factorial. As we know that NCX is equals to n factorial by x factorial into n minus 1 factorial. So here instead of n we are having p minus 1 and instead of x we are having k, where k values, as we know, it is 0, 1, 2, p minus 1. Next, the binomial distribution assumes that there are some three assumptions which are made. The number of observations that are p minus 1 are fixed. Each observation is independent. Each observation represents one of the two outcomes, that is success or failure. The probability of success u is same for each outcome. So these are the four conditions we can say, or we can say these are the four assumptions which we make to derive our theorems regarding time series. So summation of k equals to 0 to p minus 1, p of z equals to k. So we are finding the summation of all the probabilities, which is equal to summation of k equals to 0 p minus 1, p minus 1 c k, u power k, 1 minus u whole power p minus 1 minus k. So as we know that p plus q whole power n is equals to 1. That is probability of success plus probability of failure whole power n, that is number of total favorable events is equals to 1. So same we are using. We can develop a binomial distribution based method to determine the time series weight, that is w of tk. Now k is equals to 0, 1, 2, 3 as we have discussed everywhere. So k should be starting from 0 and it has value up to p minus 1. So we are deriving the weight vector w of tk is equals to p minus 1 c of k u power k 1 minus u whole power p minus 1 minus k, which satisfy the condition. We have already discussed the three conditions which we require here in the equation 2 we have mentioned. So that three conditions again we have written. So these the equation 6 should satisfy the condition, that is w of tk, all the weight vectors should be greater than or equal to 0, and k value should be between 0 to p minus 1, and the summation of all the weight vectors should be equal to 1. This is the graph shown at different values of u, that is different values of probability of success at u is equals to 0.1, 0.3, 0.5, 0.7 and 0.9. So some special time series weight derived by the binomial distribution based method are shown in this figure. Now especially if we take u is equals to 1 by 2, that is 0.5, then our equation 6 which we have derived in the previous slide can be transformed into the following form, that is w of tk is equals to p minus 1 c k by 2 power p minus 1. The time series weight, that is weight vector, derived by having the following desirable properties. So we are going to state 4 theorems regarding these time series weights. So the first theorem says that the time series weights, that is w of tk, are symmetrical, that is w of tk is equals to w of t p minus 1 minus k, as we have seen in the binomial distribution. It is similar to that. So w of tk is equals to w of t p minus 1 minus k. Since as we know that ncx is equals to nc n minus x, we have already seen in the combinations that ncx is equals to nc n minus x. So similarly here n is p minus 1 and x is k. So p minus 1 ck is equals to p minus 1 c p minus 1 minus k for all the values of k. Then w of tk is equals to p minus 1 ck by 2 power p minus 1, which is equals to p minus 1 c p minus 1 minus k by 2 p minus 1. So this is the weight vector. So weight vector of tk is equals to weight vector of t of p minus 1 minus k. So hence we have also proved the theorem 1. So that is the time series weights are symmetrical. Next, our theorem 2. If p is odd, then W of tk should be less than W of tk plus 1 for all the values of k, and W of tk should be greater than W of tk plus 1 for all k is equals to p minus 1 by 2 comma p minus 2, and W of t of p minus 1 by 2 should be equals to maximum of W of tk, and if p is even, then W of tk should be less than W of tk plus 1 for all the values of 0 to p by 2 minus 2, and W of tk should be greater than W of tk plus 1 for all the values of p by 2 to p minus 2, and W of p by 2 minus 1 is equals to W of p by 2, that is maximum of W of tk. And here we are having the proof. We are going to prove it in a similar manner which we have proved the previous theorem using NCX formula. So W of tk plus 1 by W of tk is equals to p minus 1 ck plus 1 by 2 power p minus 1 into 2 power p minus 1 into, sorry, by p minus 1 ck, which is equals to p minus 1 ck plus 1 by p minus 1 ck. So if we expand this, we can say that which is the expression is equals to p minus k plus 1 by k plus 1. So from this equation 11, we can say that W of tk plus 1 by W of tk is equals to p minus k plus 1 by k plus 1, which is always greater than or equals to p minus p of p minus 1 by 2 minus 1 plus 1 by p minus 1 by 2 minus 1 plus 1. So using this procedure, we can prove all the two conditions and the further conditions which are given in the each condition, ABC of 1 and ABC of 2. So this is the proof. So let's begin to our third theorem, that is W of t is equals to W of t naught comma W of t1 so on to W of t p minus 1 of t with the vectors of the time series weight derived by the equation 8. Then allness of W of t should be equal to 0.5. Since the time series weights are symmetrical, as we have discussed in the theorem 1, we can write, and we have also seen from the theorem 2 that if p is even, then allness of W of t is equals to 1 by p minus 1 summation of k is equals to 0 to p minus 1, that is p minus 1 minus k of W of tk. So if we simplify this term using the condition of even, if we have p as even, so we can prove that it is equals to 0.5, and if it is odd, then also we can use the conditions which we have derived in the previous slides, like these 3 ABC theorems. If it is odd, so using these conditions we can prove that p is odd, then also it is equal to oddness of W of t is equals to 0.5. So this is the proof, and we have also taken the special condition for u is equals to 1 by 2, it is probability of success is equals to 0.5, and we have transformed the equation to get the desirable output. Next, theorem 4 denotes or proves that if p is odd, then all these conditions are true, and if p is even, then all these conditions are true, similar to the theorem 2. So we have investigated the aggregation of argument information collected at different periods. Consider that the time series weights, that is, the weights of the periods, play a key role in the aggregation process of the given argument information. We have proposed an approach to deriving the time series weights. The approach employs the well-known binomial distribution probability density function and its inverse form to deriving the time series weights to derive the time series weights and derive the time series weights. Sequences are the unimodal sequences. we have discussed detailed two special cases where the probability parameters takes the value of zero point 0.5. In further work, we can develop the methods can be applied to some practical problems such as multi-stage investigation, decision making, personal dynamic examination, and medical diagnosis, etc. Thank you.